dear colleagues, good morning, buenos dias, bom dia, good afternoon, kalispera, buon pomeriggio, I think in Italian, good evening, happy IMPW, International Medical Physics Week. I'm John Damilakis and I welcome you to today's webinar. Just like in previous years, the IOMP is setting up a series of webinars this week. This year, the IOMP's regional organizations are organizing a series of 5 webinars. And today's webinar is titled The New EFOMP Protocol for Quality Control of Dynamic Imaging Systems. The aim is to introduce EFOMP's new protocol for the quality control of fluoroscopy and angiography systems. The first speaker, Annalisa Trianni, will present the philosophy behind the protocol and explain the need for a protocol that harmonizes quality control testing of these systems. The second speaker, Professor Nicholas Marshall, will focus on technical aspects, the tests, and the relevant equipment required. Dr. Annalisa Trianni is the chief medical physicist at Santa Chiara Hospital in Trento, Italy. Annalisa is an imaging physicist with a special interest in interventional radiology and computed tomography. She is chair of the scientific committee of the Italian Association of Medical Physics and director of the School of Physics in Medicine, Caldirola. Dr. Trianni has been involved in various research projects and IAEA, the National Atomic Energy Agency missions. She coordinates the working group on digital radiology of the Italian Association of Medical Physics and the EFOMP working group on quality control protocol for angiography systems. So I will stop here. Without further ado, I'd like to ask Annalisa to start her presentation. Annalisa, before starting, I would like to ask her colleagues to ask, please do not hesitate to ask any questions using the Q&A option of Zoom. Annalisa, the stage is yours.
Thank you, John. Good afternoon, everybody, and thank you for this kind invitation. I'm trying. Do you see my screen?
Yes.
Okay, so I can start. As John said, me, Nick, Andy, and other folks that probably are online spent the last few years working on this new protocol for quality control of dynamic imaging systems. Today we will present it. I will introduce the protocol and so defining briefly what dynamic imaging systems are and the different type of system available. And I will go through the challenges that building a new protocol pose to the physicist, and Nick will jump into the details of the protocol describing the tests we have included. So dynamic systems are systems that are used for obtaining visualization of dynamic processes in real time, so in the time they are occurring. And dynamic imaging systems are used for a very wide range of applications, as surgery, as gastrointestinal applications, as angiography, cardiac angiography, and so on. For that reason, the dynamic systems include a variety of different type of equipment with different clinical uses, from fluoroscopy system used as you can see here for the visualization of organs and anatomical structures, like for example the gastrointestinal procedures, to mobile C-arms and very mini C-arms used in operating theater for orthopedic surgeons, for example, for orthopedic surgery, for example, up to very complex CR systems used for diagnosis and treatment of peripheral neuro and cardiac anatomies. The system can be both monoplane or biplane, as you can see from the pictures. The systems are configured in different ways because they have to perform a wide range of tasks that require temporal sequences of images. So we mainly have two types of acquisition. One is called fluoroscopy, which refers to a temporal sequence of images to obtain real-time images of moving anatomy. Normally, fluoroscopy is not stored. Fluoroscopy is nowadays pulsed on most of these systems. The pulse rate and the frame rate vary with the scope of the investigation. Is low normally in peripheral imaging and is higher for cardiac imaging. Acquisition on the other side, which normally we call cine angiography or simply cine, is a modality that we can define at high quality, from which images are acquired and stored in packs. Dedicated equipment need to meet international standards, like, for example, the 2YC guidelines, the 6061-2-44 and -2-43, which are especially dedicated to fluoroscopy equipment on the left side and to angiography equipment, so equipment that are supposedly dealing with higher dose procedures, the 43. What is different in angio system from the other X-ray systems? They are not just used for diagnosis, but they also used for treatments. The procedures are normally very complex. That means that they use a lot of contrast media, and the procedure time is normally extended. That means higher dose because it's about long fluoroscopy times and many acquisition runs. They have different modalities like temporal subtraction. So all these differences place a tough requirement on system performances because this system needs to produce required image quality at low doses, and mostly is about the visibility of guide rays, visibility of low contrast anatomy and devices. And moreover, in the European Union medical imaging system that use ionizing radiation are subjected to the European directive, which was included in the national legislation a few years ago. And one of the requirements of the directive is that quality assurance program are in place, especially for what concern quality control, so acceptance testing and performance testing. Over the years, numerous different reports are being published giving advice on how to evaluate the system performances and proposing some different tests for dynamic imaging systems. Protocols based on this publication have been published, but typically these are from a limited working group, maybe national working group. They have to deal with national legislation. So definitely there was a need for an harmonization, so a protocol that all countries could follow. Also because the large number of QC protocols, testing methods, and limited values applied across countries is a challenge for the manufacturer, who, by the way, also published an IEC recently at the end of March, including some quality assurance and quality control tests. And also, we have done a long road since the very first and simple imaging to the up-to-date systems that we can have today, and which are much more complicated. Fluoro and angio system have greatly increasing complexity, both for what concerns hardware, so detectors, especially flat panel detectors have replaced X-ray image intensifiers, and also software. So there was not just a need for an harmonization, but there was also a need for updating the methodology that were proposed before. That's why mid 2019, me as chair and Andy Rogers, who was the vice chair, started the working group with the scope of updating and harmonizing the quality control that were available in the literature. The group was composed of members, consultants, and observers. Mainly the members work on developing the text, and consultants and observers were supporting the work. The protocol has been published last week, so it got public last week on the EFOMP website. It includes some acceptance tests, commissioning tests, and constancy tests. That's the terminology we use. So acceptance tests to be performed at the beginning, just to verify that your system is fulfilling the documentation that you required during the tender. Commissioning tests to set baseline. This is the most heavy part of the protocol, and constancy tests to verify the performance of your equipment over time. The structure is more or less the same structure that you can find in other protocols. So we have mechanical and geometrical tests for X-ray tube and generator, the automatic exposure control, the verification of those indicators. We introduce skin dose maps, even if tests are not fully complete, and there's no full agreement on that. Test about the detector and test about image quality. The idea is to have a pass-fail criteria for each test. That doesn't mean pass and fail criteria exist in absolute terms. So action levels are present only if available from the manufacturer or in literature. But mostly we set some pass-fail criteria based on the baseline values that we acquired during the commissioning. So if there is a huge change of the parameters from the commissioning, so from the baseline, then some type of corrective action is required under the judgment of the medical physicist. During this process, we face many challenges, and one is which systems should we cover? We say there are fixed engine systems, there are mobile CRs, there are surgical arms, there are RF systems, there are both flat panel detector and image intensifier. So is it possible that one protocol fits all? And that was one of the challenge. Another challenge was the number of tests, excluding image quality, which has its own place on the protocol. There are more than 20 tests. If you just think about one test, which is the patient entrance air kerma, it has to be repeated for many thicknesses, for all the relevant clinical application protocols, which is super time consuming, and we're not sure that if it's really needed. So the idea of this protocol, it is that it has to be customizable. So it has to be adaptable to different equipment, different installations, and different workloads. And the biggest challenge is, of course, as I imagine you already know, image quality. Image quality is like opening Pandora's box. You don't really know what it comes out from it. So in general, image quality change a lot with different applications. Cardiac imaging requires very dynamic images without recursive filter. Neuroimaging requires low noise and high resolution. Electrophysiology, you don't need that much image quality, so very low dose and per frame. Of course, it changes a lot with the type of equipment we are using. And at the beginning, when the equipment is installed, the application specialists, the clinicians, the radiographers, and the medical physicists need to ensure that the programs meet the required image quality. So in order to perform tasks successfully, but is successfully. So the European directive talks about adequate diagnostic information. But it's not always straightforward to define what adequate diagnostic information is. The image quality, the image quality depends largely on tasks, as we said, and the image task determines how the settings, the programs are set. But what is the best set of parameters given a certain clinical task? ICRU comes to help us. The images, saying that images generated by an imaging system are used to perform some specific imaging task and must therefore contain sufficient information for the operator to perform the task with some level of confidence. So what we have to keep in mind, and I thank you, my colleague Loredana, for this nice paragraph. It's a very nice, clear concept. So we shouldn't look for a perfect image. What we have to look for is an image good enough. Still, it's difficult to understand which is the degree to which an imaging system is delivering a good enough image. We can define image quality in two flavors, talking about clinical image quality, which is actually the goal of setting up a good equipment, and technical image quality on the other side, which is what we can do as medical physicists, what we can estimate as medical physicists. So clinical image quality is an estimate of the imaging performance for the entire imaging chain, where this entire imaging chain includes the radiology. So it's really what the radiology says. What we need is an objective clinical image quality evaluation. So we need to know the diagnostic truth. We need samples of normal and abnormal cases, a number of experienced observers, and we need to set up a rating scale. This, in principle, gives a summary of sensitivity and specificity of an imaging modality, but definitely that's not feasible for medical physicists quality control. So what we normally do is using phantoms to represent the patient, and also we use well-known methodologies like the signal-to-noise ratio, the contrast-to-noise ratio, and so on, hoping that the image quality score reflects somehow the parameter settings. Well, this depends on the degree to which the test objects capture essential aspects of the imaging text, and that's the challenge, actually. These are the issues, because we use phantoms and test objects to represent the patient, but the patient is not a phantom, and phantoms are not really patients. We don't have specific test objects, but rather we have standard test objects that can measure low contrast resolution and limited spatial resolution. These objects currently have limitations. They are mostly 2D objects. They are static objects. Smallest field of normal, they are large, so smallest field of view cannot be tested. Contrast and thickness don't vary continuously, but in a discrete way. Materials are not representative of clinical structures, and that means the image processing has a different response to these test objects compared to anatomical scenes. And also the methodology has its own limitations, because there's a lack of spatial and temporal resolution, and we are supposed to test dynamic images. These are good because they can give us a control input suitable for repeated image analysis, but definitely they cannot be used to optimize procedures. And when we decided which tests to include, we also put us some constraints. The tests need to be quick to acquire. They should work on for presentation images, because for processing mostly are not available. They do not need an export of the image from the system. They should be reproducible. The scoring should be non-subjective, so some tool like ImageJ, for example, should be used, or other home-based algorithm should be used to score the images, and typically produce image quality scores, so they can be used in constancy test. I'm almost concluding my part. Which are the tips for use of this protocol? Well, only one, actually: take judgment. So act as a medical physicist. First of all, we say this protocol has to cover different type of system with different type of detectors. So first of all, what's your type? You have to adapt the protocol to the type of system you're looking at. Second, make sure that what you start evaluating is actually the optimized equipment. So clinical staff and application specialists, together with the physicists, I've set the default settings. I've agreed on the default settings, and the imaging protocols operates as expected. Otherwise, you have to repeat these measurements again and again. Discuss which are the procedures performed, not just which is the equipment performed, in order to set which are your most commonly used protocols and thicknesses and field of view. Decide on what which are the most used protocol, and because, as we said, there are so many measurements that you can make, and definitely you cannot measure everything. And also adapt the protocol to the tools you have. Some are proposed, are included in the protocol, but you don't need necessarily to buy new tools. You can adapt the protocol to the tools you already have. So it is at the end responsibility of the medical physics expert ensuring that the frequency and depth of testing is commensurate with the imaging application undertaken on a particular system, and is not just about applying a set of pass-fail test and move on to the next system. The idea of this protocol is also that the physicists gain knowledge of the equipment and how it works based on the imaging task undertaken with the system. And I'm done with the first part of the presentation, and I leave the floor to Nick.
Thank you. Thank you, Annalisa. Before leaving the floor to Nick, I would like to introduce Nick.
Sure.
So yeah, fine. Thank you for your excellent presentation. EFOMP has very recently published this protocol, and I understand that the idea is to produce a customizable, as you said, protocol that harmonizes quality control testing of the fluoroscopy and angiography systems. This is a very nice idea, which can be perhaps copied and implemented for other modalities, for example, computed tomography. I don't know if EFOMP considers this option. But anyway, we will have, at the end of this webinar, we'll have the opportunity to discuss. And I don't know, Annalisa, do you have access to the Q&A Zoom tool?
Yeah, I do.
Yeah. Okay, thank you. So people have already started asking questions, so please have a look. Okay, so it's time to introduce Professor Nicholas Marshall. Nicholas joined the Regional Medical Physics Department in Newcastle upon Tyne in 1990 and completed his PhD in 1998. He spent 8 years in the clinical physics group at St. Bartholomew's Hospital in London, where he was appointed as medical physics expert. And in 2009, he moved to Leuven, Belgium. He has contributed to several working groups and quality control protocols over the years. Current research interests include the development of methods to assess the imaging performance of mammography and the performance of general diagnostic and dynamic X-ray imaging systems. I understand that Nicholas will present the technical aspects, right, of of the protocol. So Nicholas, please.
I'm sharing right now.
Thank you.
It takes a while. Okay, here we go. Can you see my screen now?
Yes.
Yep, I'll go to full mode. Okay, so thank you. I will continue in part 2 of this talk on the new protocol. So, well, we've already had this thing from Annalisa, how it's divided up. It follows fairly standard approach to protocols, where we start with the X-ray tube. I just put my pointer. It starts with the X-ray tube and mechanical and geometrical tests, then through the AC dose indicators, which includes like the DAP or the ACAP calibration and the Kerner calibration, and then something new, which is the skin dose map, which is not particularly well defined at the moment. But and then after that, the two big ones, probably X-ray detector, which we would like to test, but it's quite difficult to test currently due to the access to, of the image types we would like, and then image quality, which is an interesting, difficult topic. So we have a summary of the tests at the beginning of the protocol, and you can see these mechanical and X-ray tube and generator and AEC tests, which are very well defined and have quite an IEC flavor. These are kind of acceptance, or more like an acceptance test, where you check how the system has been installed, because they're probably well defined, and they will have an IEC method for doing it, and we follow that quite often. They're not really commissioning. Commissioning is more to do with how the system is performing with respect to its clinical performance, and then we can do some constancy tests with these. So it's more like an acceptance test and seeing how the system has been installed by the manufacturer or the vendor. We then go on to the other tests, which are the X-ray detector and the image quality. And here you can see that there are not many acceptance criteria because the manufacturer doesn't really supply them. It's more to do with commissioning and constancy tests. So these are more tests to do with how the medical physics department has decided to test these things. These things are not specified really by the manufacturer. For example, for the X-ray detector, the response function will vary greatly depending on the imaging mode that it's operated in and the gain, etc. The thing that will be specified maybe will be an MTF or a pixel size, which we can check quite easily. But some of the other things like the brightness uniformity or the power spectrum, they're not really specified by the manufacturer. And then image quality, the manufacturers might have their own test objects that they use. There were some IEC test objects in the past. There are standard test objects, for example, made by Leeds, which are used quite commonly, maybe also by the manufacturers. But we've also tried to introduce some new image quality methods, and I'll explain those a bit later. And therefore, these are not specified and accepted. The manufacturers won't be doing these kinds of things, but we will be doing commissioning to try and examine the imaging performance of the system, and then followed up by constancy testing. And then the famous limiting spatial resolution as well at the end. That's tested as a detector geometry and also as a system or clinical type of geometry, and I'll explain those in a minute. So each test has got its own format. It has a name that describes what we're trying to do with the test, then a reference and any supporting literature that may describe or give more detail outside of the protocol that you might want to reference. I'm afraid quite a lot of these are used IEC, IEC documents, which can be very expensive. Well, they are expensive, I know that, but they're very useful. I don't know about access. We find access to those difficult as well, but they're what the manufacturers follow because that's how their norms and standards work. Then any instrumentation. So what you would need to do the test. This test is the tube voltage accuracy. So you need a multimeter or kV divider and some attenuation. The procedure, which is how you do it in hopefully easy to read steps. And then how you evaluate. So you just check your measured kVs against the displayed values in this test, for example. And then any pass-fail criteria that you need to apply, and the frequency at which you do the test. So it could be an acceptance test or annual or constancy test, for example. So if we go on to the mechanical and geometrical parameters, which is the first set, so when you start to do QC, I think it's important to start with the source and how the source is installed, and any how the geometry of the system is working. So this is a fairly typical test, so you probably see them in quite different protocols as well. For example, determining the source location and the minimum source skin distance, where you would use test objects of a certain length and then another test object of twice that length of test object, and you image them at different distances to determine the source location. Or you look in the manual, or you look on the side of the X-ray tube to see if it's been marked, and if it hasn't been marked, ask them to mark it, for example. The minimum field size, which should be 5 by 5 when expressed at 1 meter, source image receptor distance. The beam alignment test, which is using this kind of tower with radiopaque markers, and then the correspondence between the X-ray field and the effective image receptor size. This is done an acceptance test and also done routinely, because this can go out of tolerance, and you can ask people to the engineer to reset it or correct it over the lifetime of the equipment. It will change a bit. And then there's verification of display distances, which involves measuring with a tape measure. So quite simple tests. Yes. On to the tube and generator. This is, again, standard things like the tube voltage accuracy, the minimum half value layer, or the filtration evaluation. This can vary a bit from country to country. It can be defined in your legislation, and we don't override that. Obviously, that takes precedence. So you would have to do what you would do locally for that test. And then half value layer for the clinical spectra. So this is kind of an acceptance test, or at a new tube, for example. And then this, you would, because dynamic imaging systems often have filtration that changes greatly depending on what's in the beam load. If there's, for example, if you're imaging a certain protocol and you have quite a thin patient thickness, you might have quite a lot of spectral filtration, or copper or tantalum filtration, for example. And if you go to thick, large patient thicknesses, that will be gradually removed. So the half value layer is changing all the time, and you want to evaluate those at the commissioning test, so to see that the HVL is changing appropriately. Then there's a normalized air coma, or the yield, or you might call it the tube X-ray tube output, measured at about 80 kV, and then leakage radiation. This may or may not be done by you, as in diagnostic X-ray physicist or medical physicist. It may be done by some other department, like it's done here in the hospital by other colleagues. So, but that is specified in the protocol. These tests, we know, can be, I mean, we've done these for years, they can be difficult to measure, as all dynamic imaging systems have AEC control, and these days it's very hard to turn the AEC off. Ideally, we'd want a manual mode or use a QC mode, and they are available on some systems, but it's few, and you may have to pay for those modes, or specify them at the tendering stage, where you have this QC user QC mode. So you need some tricks to be able to do this, where you take filtration and you place it behind your multimeter to make the system change X-ray factors, so you can measure the kV and measure the yield, etc. At different tube voltages. So, and when you're doing this, it's very important to remember to protect the detector. Yeah. Onto the automatic exposure control. So, a brief reminder what this job of the AEC is. It's to automate the selection of X-ray factors to cope with changes in patient thickness as you move and make different projections around the patient, to provide a consistent and adequate image quality for your current task, which, as we know, can be programmed for the different tasks. So this means really maintaining acceptable levels of noise, contrast, sharpness, temporal blurring, so that the clinician can get the information that they need to do the task. Keep the system operating safely, i.e. within the technical limits of the X-ray tube, so you don't destroy the tube by going to factors that are not, well, just dangerous or not appropriate for, will harm the tube. And keep the system operating within regulatory limits and, in fact, following the ALARA principle. So it's a very important, we could call it component of the imaging system. It's crucial, actually. It plays a huge role in determining the dose and image quality balance. They're very flexible, as Annalisa showed earlier on. These fluoro or dynamic systems can be used for a great range of tasks, and this AEC is programmed to switch parameters and settings for the different tasks. It can be doing fluoroscopy, some cardioangiography DSA at a certain frame rate, and they all require different programming in terms of how the X-ray factors are selected as patient thickness changes. And it's really important that you have some idea of how the AEC works on your system. It will be different a bit between different manufacturers and between different types of system. It could be simpler on certain like fixed, well, small mobile C-arms, for example. It will be a bit more simple than large interventional suites. The system will have control over a number of parameters, and this will depend on the imaging system. It will vary the kV, the tube current, the millisecond or the pulse length, the focus size, maybe the copper filtration as patient thickness changes. And it's really, I think you need to find out how your system is working so that you can test it properly, and also how the acquisition and the fluoroscopy modes are related. So you might select some acquisition mode, and then that will program some kind of fluoroscopy dedicated to that type of acquisition. And if you change to a different acquisition program, then the fluoroscopy mode will change. And then there'll be sub-modes within the fluoroscopy. So you could go to low, normal, or high within those modes, or yeah. So yeah, understand your AC. And the way that it's done in the protocol is that we do an evaluation where we just vary the PMA thickness in comparison, and compare the factors selected by the system in comparison to manufacturer data. So we need PMA sheets, quite large sheets, 30 by 30, maybe 1 centimeter thickness or 1 or 2 centimeter thickness to cover the total thickness from 5 to 40 centimeters. You can see this is a large thickness. When people do ACs, normally you think about 20 centimeters as your standard thickness. It's probably a bit too thin for a lot of imaging systems. This 20 centimeters certainly for interventional and cardio. It's closer probably to 30 centimeters as a standard thickness, and certainly even higher under some projections. But the aim is to test the most commonly used modes. You can't do all the modes. I mean, there'll be 50, 60, 70 modes on some systems or protocols. You can't do those. You need to know which are going to be commonly used, know which system acceptance, which modes the manufacturers supply data for, and make this measurement. Okay, and to do the measurement, you position your PMMA, for example, on the table. It says start with 15 centimeters for like adult programs, do some X-ray, like fluoroscopy, record your factors. The actual factors you can record may vary, might not. Some systems may not show all of this information immediately. You may have to go to the SR report to find it. It can be quite hard to find on some units. Some systems it's clear, but you need to record these factors and then keep adding PMMA until you get to the maximum PMMA thickness, which could be 35 or 40 centimeters, depending on how much PMMA you have. And then do this for all the commonly used clinical modes for a standard field of view, like Annalisa suggested. So like maybe 20, 25 centimeters, or even 40 centimeters, 42 centimeters for large, like body DSA, for example. You might want to test mobiles in the lateral projection because you can't put all the PMMA on the detector itself. You have to support it in some sense. You may not have an appropriate couch, an X-ray couch, so you may find a table and support it laterally for living mobiles. And then once you've acquired your data, then you need to plot the technique factors as a function of PMMA thickness and critically examine what's going on with the system. It tells you an awful lot of information of how the AEC is programmed. So you can see on this system, the PMMA has gone from, this is in the protocol, this graph. So it goes from, say, 1 centimeter, I mean, up to more than 35 centimeters. And you can see how the system changes the kV. The kV generally is pushed up as you increase to get better penetration through the patient. At thin patient thicknesses, there's a lot of copper pre-filtration. This is then dropped down as the patient gets it, so removed because you need more tube output. And then you can see that the MA it's related to the focus size bands. So here you will be on the micro focus, and then it may switch to a small focus, and then it may switch at this point to the large focus, and that's where you need the maximum amount of power to get through the patient. So this gives you an awful lot of information, and it also helps you, in effect, understand the system and to help in optimization, comparing one setting against another setting, but it takes quite a long time to gather this information, but very useful. You also do the commissioning test. You measure the incident air coma rates as well, and this should be done for fluoroscopy and for acquisition modes as well. And then for commissioning, after commissioning, you do some extra measurements where, for example, you might fix the PMMA thickness and vary the mode and the field of view, and then fix the mode, vary the field of view, and vary the PMMA thickness. So you do some kind of variations against which you measure the air coma, and then compare your measurements, for example, the dependency, and also how things have changed from how you set at commissioning. And you expect a 20%, at the most 20% deviation from the baseline. So this is quite standard AEC testing. This is like characterizing the AEC, and then this is looking at its performance as a function of thickness or field of view, for example. But only
Nicholas,
yes?
Can you please hide the bar, the stop
thing.
sharing bar at the bottom? Yeah, thank you. Okay.
Yes. Next one. I will say that fluoro tests may, AEC tests will probably change in the future as well. I mean, since we were writing the protocol, manufacturers have started to release new systems where they have these task-based control methods, where, for example, the system is measuring or estimating what the CNR would be, the contrast to noise ratio, or a modified version of that, and then setting the X-ray factors required to achieve that contrast noise ratio. For example, in Siemens have the Optique, and GE have auto-write, and in the Optique system, the operator specifies what you're looking at and what your target will be, the composition of it. So it could be iron or steel for a guide wire. It could be a tantalum marker in a stent. The size of it, so a guide wire thickness might be, say, 0.36 millimeters. The velocity of the object, for example, in cardiac, maybe 20 to 30 millimeters per second. And then the AEC searches some kind of pre-calculated parameter space and finds the X-ray factors that deliver the target image quality for the lowest incident air coma. And you will have more AECs that do this. And to be able to evaluate these, we will need new types of test objects. At the moment, this characterization that I showed earlier on doesn't have any test objects in the beam. It just has PMMA. And we should probably have some details in there that have some kind of composition that's relevant to the clinical tasks like iron, barium, tantalum, iodine, etc. And we will need test objects like this. And there's a working group in the AAPM looking at this, and there will be a report coming out soon, I think, on this. I'm not going to say very much about dose indicators because I'd like to get on to the image quality. But obviously we test the things like the air coma area product display accuracy. So you make an explicit measurement of the air coma and the field of view and calculate yours, compare it to the one that's displayed. Then the manufacturer air coma rates, and measure it using manufacturer geometry and dosimeter position and compare what's on the screen compared to what you have. Measurement of the table and mattress attenuation. Again, these are kind of IEC specified manufacturer specifications that you will compare against your measurements, okay? Limiting air coma rate, this is where you drive the system to its maximum air coma rates and measure it, and then calculate with an inverse square correction the air coma to what it would be 30 centimeters in front of the detector input plane, excluding backscattered radiation normally. There may also be some other kind of local or national regulations that you should follow or may have to follow. That will depend locally. Then we have these pass-fail rates, for example, the 88 milligray per minute for normal mode and 176 milligray per minute for the high dose, a factor of 2 higher. Or there could be some manufacturer setup that you've requested that limits this to lower than that. The skin dose map. Yeah, I'll give a quick summary of this. This is still a bit, I wouldn't say work in progress, but a lot of systems have this skin dose mapping where it has a model programmed into the system where the system predicts it measures the geometry, the distances, the field of view, the factors, and it predicts what the peak skin dose will be on a model of the patient. and we want to verify this model, as in, and yes, so the first step is to see, you need a manufacturer calculation model from them. So you need to actually communicate quite closely with the manufacturer, ask for their calculation model. You set some views and projections, measure the X-ray factors, you put those into the model offline, and then see that the system is displaying the things that you've calculated with the offline method. I think that's how that works. Someone will correct me on that if that's wrong. And then there's the commissioning, where you would actually measure, again, do some geometries, put a patient equivalent phantom on the table, do some projections, and then measure the actual peak skin dose using, for example, strips of film or TLD or something, or a dose meter, and then compare that with your the SDM calculation that's given by the system. So, but this is still, as you can tell, not to say work in progress, but it's still to be tested how well we can do this. So, but some kind of verification of the SDM is needed, I think. I'm going to go over time, I'm afraid. So I will say a little bit about the detector, but I will go a bit faster through this. I'm sorry about this. So we would like to test the X-ray detector, and one of the ways you do this is with Fourier metrics. So this is like the modulation transfer function. That's the wrong way around. The normalized noise power spectrum, maybe the DQE, maybe not. And this requires well-defined beams, known X-ray detector exposure levels, etc. To do this, you need a QC mode. So you need the NEMA user quality control mode, where you can set X-ray tube technique factors, and you can acquire 4 processing images from which you can calculate. And then you measure these things like the response function, the MTF, the brightness uniformity, noise decomposition, for example, or power spectrum. These are all described quite carefully in the protocol, so I'm not going through them here. You need a nice clean geometry for this with metal filter, normally RQA filter or 2 mil copper or 1 mil copper or something like that. Put your test subject at the detector. And then you can also do it laterally if you want. And then you get the graph like this, like a response function where you have your pixel value versus the air kerma that you vary at the X-ray detector, your noise power spectrum, which you can measure at repeated states throughout the life of the detector to see how the noise is changing quantitatively in the X-ray system. This works very well in mammography, so I don't see why it shouldn't work in dynamic imaging. And then there's the MTF, and here you can see the influence of binning. So here's normal smaller fields of view, and here's the large field of view which has binned. So these are useful detector characterizations, but it's not as straightforward as it may seem to measure this. Which mode are you in? I mean, do you measure fluoroscopy or cardiac or series imaging? Do you know the gain of the detector? You probably don't. Is the gain the same as it was last time? I mean, the detector has got lots of different modes, and you hope that it goes in the same mode each time you go into to measure. And our experience of it in normal imaging is that it does, and DR imaging and mammo. But in fluoro, it's more dynamic in fluoro. I know that acquisition has got a lower gain than the fluoro. Okay. Can you set manual technique? We've discussed that already. Do you have access to raw data? So yeah, a big problem. We can't do this on most systems at the moment. What X-ray beam should you use? And then do you need to do lag correction? This is only really important if you want to measure the DQE. So, and remember, it's just the X-ray detector. So it's not image quality as such. It's an important aspect of image quality, and it sets the noise and the sharpness to some extent in the image along with the selected dose rate, but it's just a detector. So when we come to measuring technical image quality, you have a choice of 2 geometries, and the protocol describes this, either use of either of these geometries is described. It's not very well put, sorry. We would focus on this one because this includes a lot of aspects of the system that will influence the technical image quality. It will include geometric focus blurring, because your targets are here and will be subject to focus size and focus motion blurring if the object is moving. Scattered radiation, so how good is your grid? Influence of the anti-scatter grid, I just said that. And then the X-ray energy that you're using. So high energy tends to reduce the contrast. Well, it does. And we've specified 4 methods. They're kind of contrast detail based or low contrast resolution of the detector. And there are some limitations of the test objects, which I'll discuss briefly at the end. But we're extrapolating results from the technical image quality test to a clinical image quality. And that is quite difficult to do. As Annalisa said, the technical tests are, and the test objects are quite limited and don't fully simulate patients to any degree, really. So there are three main calculated methods. So we want to go from a visual image scoring method, which is subjective and has problems comparing against standards and comparing against other colleagues, for example, because you have to count how many discs you normally you would see, to a calculated method where you have access to the image data and you calculate your result. The first one was developed by Marco Tapivara and Michael Sandborg in a series of papers, and it's based on a model observer. It's a DC suppressing, high frequency suppressing model observer. It requires well-defined targets that are added or removed from the image. So you measure, I'll explain in the next slide how you measure it, but you can choose actually what you want to use as a target. It can be aluminium or iron or bones simulating material. And it's not a threshold method. So you have something that's quite clearly visible over a range of phantom thicknesses, not too visible, but clearly visible. So you select your geometry that you want to evaluate, your protocol, your field of view. You need to establish how many fluoroscopy images that you can store from a single run, because you do fluoro and then you store the images. You need about 1,000 images, so that if you can do a 20-second fluoro store, 15 frames a second fluoro will give you 300 frames. You need to do 4 fluoro store sessions to get the images that you need. And you need to do that for signal present and signal absent. So you put your test object in, for example, a bone detail like this, perform fluoroscopy, record the factors, store the images, and then remove the test object. Again, perform fluoroscopy, store the images, take the images from the system, and then go and calculate it using some MATLAB supplied software. Supplied MATLAB software, and then calculate your signal to noise ratio rate. This actually describes the accumulation of information in the image. It's well defined in the papers by Michael and by Marco Tapivara. So, and then you can repeat for other protocols, fields of view, thicknesses, for example. But it's quite, I wouldn't say quite time consuming, but it probably could be if you're doing a lot of different settings. And here's an example of the output. So you have the background image from some frame, signal present, signal absent, then the template that is then applied or calculated from, and then you can measure the signal to noise ratio rate over time and see how it varies with dose rate. And Michael has done some work on this, published in Radiation Protection Dosimetry, where you can read more about it. But you can measure within about, well, between 6% and about 14% to 2 standard deviations for a well-defined QC setup. So it's a very reproducible method. The next one is to use something called a statistical method developed in Italy by Nicoletta Paracchini. I'm over time, sorry. And this statistical method uses a small aluminium test object where you extract ROIs from this of different sizes. So you image it with PMMA, for example, or even with metal filtration. You image it, you acquire fewer images. You only need, I think, about 30 images to do the calculation. And then you extract ROIs of different sizes from this this region here. I think we see it next here. Here's your image of this. You extract ROIs of different sizes in here. You use the measured values, pixel values, in the stepwise to convert it to an aluminium equivalence, and then you can calculate a contrast detail curve for different fluoroscopy modes, for example. This uses fewer images than the SNR squared method, but it's basically just using the noise in the image. If you can see that there's no target here. And then the final method is the described by Marco Bertolini, based, I think, or developed from a model observer developed at the Mayo Clinic by Fabazza et al. And Ken Fetterly. This is a channelized to telling observer method, and it's applied to the readout of contrast detail test objects. So these test objects are used to generate the contrasts or the targets in the image. So you get, again, it's signal present, these targets, and signal absent acquisitions, and you can make a template and calculate, well, a decision variable by applying the template on the images. And then this is calculated for detailed diameters from 4 down to 0.35 millimeters in the test objects. You can use leads TO10 or TO12 for fluoro and angio, or TO16 and TO20 for angiography. Like I said before, you choose your geometry and protocol that you want to evaluate, place the test object on the stack of PMMA, image it, then remove the test object. You may need a blank if your factors are going to change. So if your factors do change during fluoro, you would want to put the blank plate in so that you have the same factors with and without the test object. Store the sequences. I think you need, I'm going to say here, about 400 images for this. So, and then you indicate on the test object where your targets are, the system segments, the software segments, the signal present, signal absent regions, and calculates your threshold contrast. For all three methods, this threshold contrast that you evaluate, or signal to noise ratio rate, should be within plus or minus 20% of the baseline value for your mode. And here's an example of the Marco's method. So he has a CHO analyzer. This is TO10, I think. Then you segment these signals from here, and then you generate a contrast detail graph. So finally, you can do visual scoring, but I won't go into that because we don't have time. And also you can do line pairs test object, so a sharpness test. And that can be done in the detected geometry or with a scattering material placed at the patient position, so you include some geometric and sharpness as well. So yeah, I'm a bit over time, but I'll make a point about the image quality itself. The computational readout will give a more reproducible estimate of technical image quality, and I think that's very good if we want to test against performance standards, because visual scoring between different groups, between medical physics departments, between countries even, will be different, and even between you scoring one day to the next day, there will be some variation. There'll be less variation if you have a computational readout. So that's a good thing. Task realism, you've seen that the tasks are very simple at the moment. The object sizes, you know, do we need to extend to guide wires or stents or markers, and what are they made of? I mean, what's in the least test objects? It's not known really. It's probably copper and aluminium and something like that, but really we want something that is either bone, iodine, tantalum, platinum, whatever is in the the details or the objects that are used by clinicians in the to do the tasks, to do the treatments, for example. Object motion is the big one. It's not really in. If you want to do cardiac evaluation, then you have to include a moving test object, and that's not in at the moment. So, and then also a big thing, image processing. As Annalisa said, the test object should trigger the correct image processing, but really we have small details in a homogeneous background, and it's probably the image processing is not really behaving as it would be clinically. So a summary slide. There are many different approaches, and we've tried to harmonize. We hope we've helped in that respect. Systems have increased complexity, increased flexibility, and we need to understand how they function if you want to make meaningful assessments. The protocol emphasizes the need for relevant QC, so understand what tasks are done on the system, what imaging modes are used, and evaluate those imaging modes. We would like routine, easy access to full processing images so we can calculate or evaluate the detector. And that really could be quite quick to do if you had those modes easily available. And then image quality evaluation is challenging and will be I think for the foreseeable future. But we need to work on test object design and methods of evaluation. But I think it's a good step to move towards computational methods to evaluate technical IQ. So thank you. I'm sorry it's a bit over.
It is. Thank you, Nicholas. A great webinar with more than 1,500 participants. Very impressive. And before getting into, well, I will prolong a little bit this webinar by 5 minutes. Just there's a long list of questions. Actually, it's impossible to discuss all of them, but at least a few. Yeah, we need to discuss.
Maybe
before getting.
Sorry, John. Maybe some of them can be actually merged.
Sure.
together.
I will try to do that. Well, we cannot extend it, so only for 5 minutes perhaps, to be able to discuss few of them. So before getting into the question and answer session, I would like to thank Magdalena, Professor Magdalena Stoeva. She's behind the scenes, taking care of everything, even after the webinar, for the recording. And of course, you can, colleagues, visit the IOMP's website to watch the previous webinars. So the first question, well, I'll start from the first question. First come, first served. So it's very specific. It's about OARM. I think it is for you, Annalisa, because you said something about OARM.
Just mentioned them. I'm not really familiar with this.
Indeed. Just for those for those who don't know those systems, and they have a navigation system which scans the spine during surgery, and the system creates images and helps orthopedic surgeons to, for example, to insert pedicle screws, or for kyphoplasty and vertebroplasty procedures, and so on and so forth. So the question is, what is the role of medical physicists in making sure that these systems, navigation systems, are performing well, and what kind of tests should be considered? I don't know if you have an answer, Nicholas or Annalisa. These are very specific systems. Have you ever tried to check, perform any tests?
Not me, at least.
We had one here for a temporary installation, and it was indeed it's a challenging thing to try and test. You can test the normal fluoroscopy aspects of it, you know, in because it will do planar imaging as well, and then actually one of the main things was to do with the radiation safety and the leakage, because it was quite hard to situate it in an operating room. So that's a whole practical aspect as well. To be honest, I don't really know how to test that properly. I mean, I think you would need some, if you're going to assist in you know, image guided placement of screws and things, then you need a test object that is quite dedicated to that, I think.
Indeed.
And, I think it's a bit like doing you know, stereotactic unit on a mammography system. It relies on a good geometry test, and you can do the normal fluoro QC, but the actual things that it's in, the tasks it's designed for is it's hard to evaluate with a generic test, let's say. Sorry, it's not a very good answer.
No, it's a gap, actually. To the best of my knowledge, there is no any commercially available test tool.
No.
So good to know for version 2 of your protocol, maybe.
Well, but then how much time do you spend developing a very elaborate test for where there are only 1 or 2 systems? You know, it's a case of balancing what you
maybe
have to
later
do.
we will have more systems. Anyway, there are a couple of questions about the periodicity of quality assurance tests, and a question about private companies. What is your opinion? Can private companies perform quality control tests?
Quality control are outsourced. Why not? I would say, as long as they are independent, because in the directive, all is about independency from the manufacturers.
Independent of the manufacturer.
You should have independent tests. And I think there was also a question about this from someone from Sweden. I can really find it now, but he said,
I think you have already answered it. How much manufacturer involvement is that?
No, it's our manufacturer involvement. We had a constant connection with the manufacturer, especially because Andy Rogers was also involved in the development of IEC, and me as well. So we were following that from close. But there's a question in Sweden. The trend seems to be to leave the acceptance and constancy test to the supplier of the system, and rather validate the supplier test to see if the test cover hat should be measured and if the results are satisfactory. Your view on that? Again, The directive actually requires an independent test from the manufacturer. So that's our answer. And about frequency of test, it goes back to my final slides, take judgment. You really need to adopt. Well, we give suggestions, but medical physicists really need to adapt the protocol to their needs and pick up the tasks they think they are most important for their equipment and the procedures they perform.
Two more questions, please. Just to, there is one question or two about clinical image quality and technical. I understand that the Arun Chugle means the objective and subjective, perhaps. So the question, is there any linear relationship between image quality, subjective and objective, or what is the relationship?
Well, we hope, but there's not.
This is the one from Arun.
It's a dream.
Yeah, I mean, you would expect if you change aspects of the, let's say you change the energy or the dose rate or whatever, and you change the noise and the contrast in the image, you would expect the performance of the the task performance to change in some way. Whether I don't expect it to be linear. There'll be some region where, it's a very hard question. It won't be a linear correlation. You'll be able to set the system up where you won't be able to do your tasks. Okay, you just won't be able to. You might have a too lower KV. You'll have no penetration through the patient. It'll be too noisy. Your task performance will be awful. As you increase your reduce the noise, increase the penetration, improve the contrast in the image, you will start to be able to perform, and it depends, I mean, let's leave dynamic out of this. You'll be able to perform the task with increasing success. And then there'll be a point where you'll have very high quality images, very low noise, very good contrast, very high patient dose probably, where you actually have effectively too much information in the image and your task performance doesn't improve to any great degree, and then you're operating at too high a dose. So you see these graphs where you kind of go up, you're on a certain curve where where this region where task performance and some technical parameters like contrast, noise, resolution, etc., are affecting the performance, and then you'll get to a point where it flattens off. And then the hard part of optimization is trying to find this combination where you at some like guaranteed success rate or with some kind of let's say overhead that the different clinical tasks that you have to do will vary in difficulty. So you want to be able to do the difficult ones and therefore if you can do those, you'll probably have too much image quality to be able to do for the easy ones. So you could have used an easier setting or lower doses, etc., for the easier tasks. But you have to set. It's kind of statistical. You need to go have a general setting that works for most of the tasks that you want to do on the imaging system. And that's the idea of fluoroscopy systems, is that you have these dose mode changes. So if you're having difficulty, you can go up to a higher dose mode. Or change frame rate, for example, if you're struggling on a certain kind of patient with a certain view. So, yeah, it's not an easy question, but it won't be linear. It'll only correlate to some extent in a certain range. Is that okay? A bit garbled.
Yeah,
Sorry.
Definitely. Thank you, Nick. The last question. I'm trying to integrate. There are questions about the automatic exposure control curve. Do all manufacturers provide that curve, and why do you recommend, another question, doing a comprehensive evaluation of the functionality of the automatic exposure control as a constancy check? This seems to be an acceptance or commissioning test. That's our colleague. That's how our colleague sees this specific evaluation of the functionality of automatic exposure control. So first, do all manufacturers provide the curve?
Not really.
No.
No.
In the
I'm
old
not
days,
surprised. Yeah.
let's say Siemens had a range of curves like, C63 or C90 or whatever, where it would have a defined relationship between the kV and MA. But these days, the systems are very, very
Complex.
kind of flexible, and those curves don't exist anymore. The system is always finding its, its parameters that it needs to set. It's got more freedom to do, to work, I would say. But I would agree with the comment. I think if you do a very good acceptance or commissioning test, then I don't see why it really should change. But there could be changes to the AEC programming over time.
Yeah, they could be,
do spot
especially
checks,
if they're,
maybe.
yeah, especially if there's an update in the software
Yeah,
version of the equipment.
for sure.
So something can change, and it's difficult to track all the changes over time of the equipment because normally are not, I mean, the medical physicist is not directly involved, but he is involved through the clinical engineering department. So sometimes, or the manufacturer do it during the maintenance program. So that's why we decided to include. But again, it has to be adapted to the local situation.
Yeah.
And one other thing I wanted to answer, I see 2 or 3 questions about that. Yeah, the 3 programs for the evaluation of the object included in the protocol will be uploaded, and so it could be downloaded for free from the EFOMP website.
Great. 12 minutes passed, so I think everything has an end. We need to close this great webinar. What a great way to start the week. So I would like to thank both Annalisa and Nick for their outstanding presentations, and of course all colleagues, 1,600 colleagues for participating. See you tomorrow. Tomorrow is another day, another webinar. So bye-bye. See you tomorrow.